Welcome to Paul Physics Classroom. In this episode we will study how to implement ODEINT package for solving second order differential equation. In the earlier edition we have solved first order equation. Please go through that video. The link of that video is given in the description as well as in the I button, and I am just giving a brief review how to implement that, the basic theory behind it. ODEINT function can only solve ODEs of this form, that is d sum x vector or matrix. I will explain it later. dt, that is equals to sum f xt, which is kind of a matrix or vector, whatever you call it. I will explain it later, of this form. And any explicit ODE can be transformed into this form, which will be discussed in this lecture. Let us consider the problem of this form. It is second order equation. Say it's a harmonic oscillator problem, or you can treat this as any general second order differential equation, any kind of, any sort of, without any physical meaning attached to it. That means m d2x dt2, that is equals to kx equals to 0, and x at t equals to 0 is x0, and dx dt at t equals to 0 x0. These are initial values. These are initial values of the problem. Now transform the equation as x equals to x0 and dx dt equals to x1. Let us consider, we just assume this value. Therefore d2 that means x is x0, the dx0 dt equals to x1, and you take the double derivative of this equation. That means d2x dt2, that is equals to dx1 dt, right? Therefore m d2x dt2 plus kx equals to 0 becomes m d2x dt plus kx0, that's equals to 0, and dx1 dt, that is equals to minus k over m x0. This is one of the equation, and there is another equation dx0 dt, that is equals to x1. Therefore we can say dx0 dt, that's equals to x1, this is one of the equation, and dx1 dt, that's equals to minus k by m x0. That means our basic equation m d2x dt2 plus kx equals to 0 can be recasted into two first order coupled equation. Coupled because x1 here is a derivative and x0 here is derivative in this term. It is x0 here. They both are coupled and both are first order. Therefore we can here x bar is an array with two entries, and fx comma t, x vector comma t, which returns an array with two entries. That means f is equals to x1 and minus k by m x0, and x vector is x0 x1 with the derivative of that thing. That means derivative quantities, and f is equals to x1 x2. So therefore I can recast this. You remember that I will always say the ODEINT always use of this form. I have converted our equation into this form. Therefore ODE can be recasted in any way, or ODE can be recasted in this way. An ODEINT function, say x equals sum x equals to whatever may be the variable here. ODEINT equals to f, x0 and t. Only minimum 3 inputs are required for solving ODE using ODEINT. F is a function, and x0 it is a function I will discuss while implementing, and x0 is the one dimensional array with initial values of x. X means x vector, that means x0 the first thing, and the derivative of that thing is x1. You have to assign this in the x vector, that is x0 vector, and t is the time slice, the array of time over which you are computing x and x function of t, and it will return an array for two-dimensional second order, rather not two-dimensional, second order kind of thing. It will consist of two values, array of values with two columns. First column contains xt evaluated at the values in t. That means it depends on the t arrays, and in particular this value the xt will be computed. And the second column contains the derivative of x0, that means x, that will contain. And if it is a higher order differential equation or third order or fourth order, that means the third column will contain d2x dt2 and the fourth and so on, in this way. Now in this way any order that can be solved. Yeah, and you have to first you recast this in this way by variable transformation. Now we are going to discuss how to implement that in Python. The next part of this lecture, that is very vital, that is the main aim of this lecture. And first we have to import numpy as np. These are the library files, scipy.integrate, and from the integrate there is a function that is called ODEINT, and is a integrate in the module, integrate module, and import matplotlib.pyplot as PLT. Now first I define the parameters of this problem, and if you just go there, go that lecture, and you can see, and I have given a problem here that we want to solve using Python. M d2x d2, that is equals to kx equals to 0. Say x at t equals to 0 1, and d2x d2 at t equals to 0 is 0. That means x equals to x t equals to 0 1, and dx dt equals to 0, and k equals to 1, m equals to 1. And for that differential equation, for this differential equation, exact solution is cosine root of k by m multiplied by t. And we have to compare our exact result as well as numerical result. First we try to implement this problem here. How to do that? Import numpy as np, and from this thing I have already discussed. First I define the parameters. Parameters k equals to 1 and m equals to 1, and after that we need to write the initial condition. What is initial condition? I want to make the problem as simple as that. I do not make it much more cryptic or something very much encapsulated in many things. I am just writing this program keep in view for the first learner. Initial conditions are there. What is initial condition? That is x, say x underscore 0, x0, which is say 1 according to the problem. This is 1 at t equals to 0, and another quantity x underscore 1, the first derivative, that is equals to 0. This is the first definition, and this is the second. And I am just packing this. I am just pack this as an array. Is a capital X naught. I am calling this, and that is basically these two quantities. This is an array where these two initial conditions will be there. Okay, and just check it. Just every time you check that this is 1 and 0. This is an array containing the initial values. Now we just define a time over which we want to solve. Say t equals to np dot range 0.0, so times 0 to, this is not time actually, this is any variable t, this variable t, independent variable t, but in this problem x is position, dx is velocity for physical meaning, because it has a physical meaning, and t is time, so I may call it time, but it is not actually. In general problem it is not time. Anyway, you understand the fact. 20.0, say in the spacing, say 0.001, that means 0 to 20 with point spacing 0.0, it will create a time array. Just check the time array. This is a time array. Okay, this is a time array. I am just not checking all the times. Okay. Now I have to define a driver function. What is driver function? That is f function, driver function for ODE. What is that? Def some function f which needs two things. Some x, which is first condition initial, and then it will iteratively expanded, and just check it. X naught, first value is x naught, say, which is, it will accept an array, and this array basically will be inputted here via ODEINT, and therefore the first value of that thing, x0. And what is x1? What is x1? I do not make this variable same. and this is your x1. No issues, but I will definitely, and this is your x1. And first you have to convert this thing as dx0 dt. The first derivative will be that is equals to x1. You just look at it, that is equals to x1, that is equals to x1, and the second thing is dx1 dt, that's equals to minus, and two things needed, k and m. Here k and m is a global variable and it will be accessed from here, and therefore minus dx1 dt k over m multiplied by x naught. I hope so. Okay, and it will I have to return two things. The first thing is I have to return an array which is dx0 dt. The first column contains the dx0 dt, and the second thing is dx1, the derivative of x0, that thing. Fine, this is my driver function. Now I have to call ODE solver. What is ODE solver? That is ODEINT, ODE solver. What is ODE solver? Say that is xv. The container is xv, ODEINT, and first thing is the function f. I will call the function f with the values of x naught. X naught is this value. This is the initial condition, and the time slice t. Fine, best complete. And if you just, this is the first array contains the integrated value of dx0 dt, and the second column contains the integrated value of dx1 dt. That means this thing that I have basically this integration of this dx0 dt, that means x position, and this is the with respect to dx dt. Okay, now we want to plot this, and how to plot we know, plt dot plot t comma xv variable, the first column, just check it. Wow, that is your position, and that is your position. And now if you plot the exact thing we know, x cosine of this thing, plt dot plot at the same time t, and here that will be np dot cosine np dot sqrt a over m multiplied by t, and it will be plotted by, say, red dash line, and mark every, say, I will just check it first. Check it. Wow, that is not clear. Both are superimposed, so you can make it much more. Say mark every 100 points, mark, or rather you here use color is say O points, O, and color is K, and mark every 50, mark every equals to, say, 50. Not all the points will be marked, and label numerical, ODEINT numerical, ODEINT numerical, and plt dot for making it plt dot grid true, and then plt dot x level, what is that? This is your position, this is your time, and this is your time, and then plt dot y level is position, and this is your, this level is analytical results, analytical, and plt dot legend, location set best. It will decided by the Python matplotlib package. And last plt dot, it is not required here, but I am just for completeness I'm writing it here. Wow, this is your that matches, this is your the result. And if you look at the diagram and make it much more dense, so I just make 100. Wow, this is the black dots are numerical values, and the red continuous dash line is numerical, this is analytical result. Both matches exactly. That's a very great result, I think so. And therefore, if you want a velocity versus velocity versus time graph, then you just, I'm just copy it and paste it and make this thing first column. This is a 0th column, that means first column. This is a second column, that means 1. And it is velocity, the level is ODEINT numerical. There is no analytical result right now, but you can do that. I am just making numerical, which is the velocity, this velocity curve. This is your velocity, which is computed as a numerical, and this is velocity, and just check it. That is very vital. That is the first column, that is second column, this is your first column. 0 means first column and 1 means second column. Second column contains the first derivative of x0. And you can also plot a x versus v. How to do that? You just copy that thing and you change that thing as I say position versus velocity. That means phase diagram, position versus velocity. And how to do that? And I can do in this way. First column contains position and second column contains velocity. Position versus velocity, I am just, this is called the phase plot, and we don't require this thing at all. And this thing is phase, and you can label that thing. Just copy the code and edit it. This is your x position, is x axis is position and y axis is, y level is velocity. This thing, I hope you understand. And this is your phase diagram, and you can also label that thing phase plot. And so therefore plt dot legend location best. Fine. This is your phase plot, and you can make many ways. This is going. This is your phase plot. I hope you understand how to implement the second order differential equation. If any confusion, please comment us in the comment section. And if you have any criticism or anything, you have advice or any video requirement on Python or in physics, you just write it in the comment section. Thank you for watching this.